What's that, ghost of Albert Einstein? You want to analyze graphs of polynomial functions? What a coincidence. That's what we're doing today. Here in 6.8, we are going to look at what these crazy graphs look like. Okay, so in a nutshell, this is what's going to be the meat and potatoes of everything we're doing. Here, a 0 is defined by if I plug it in, the output f of x thing is going to be a 0. So when I have k is a 0, it just is saying, okay, if I plugged in this value, say I plugged in a 2, then I get a 0 as my output. A factor is going to look like x minus k. So again, as we have these things, something is a factor if when I plug that k value in, it's going to 0 out because then I get my 0. So this is the stuff we're looking at before, where if it looks like this, okay, that's a factor set equal to 0. So if I'm able to fully factor this thing, I get a whole bunch of them. So like for this one, it would be x equals -1. But let's say I had a couple of them together. Let's say I had one that was x plus 2, and I have another one that's x minus 3. So again, we would say this thing is factored. We would say this is a factor, and this is a factor. For this factor, my k would be -2. So I solve and get that value here as -2, and here I get my k value is +3. So again, if I plugged in -2, or if I plugged in a 3 into this equation, it's going to give me a 0. So we can see how we go from our k's back to our factors, and from our factors to our k's. A solution, so k is a solution of the polynomial function when f of x equals 0. So the x value we're plugging in for that k zeroes out our equation. So if k is a real number, then the following is also the same thing as saying it's an x-intercept. So if I've got some imaginary solutions for k, totally possible, it's just that it's not going to be an x-intercept. So again, when we talk about zeros, here we're talking about our xy coordinate system here, and like for this one as an example, I've got one at -2. Oops, let's do it in the same color so we're staying consistent. So I'd have one here at -2, one here at 3. Again, not the greatest graph the world's ever seen, but there we go. So as we look at this thing, again, where it crosses is an x-intercept, and those are always zeros. So a coordinate point here would be -2, 0. Likewise over here, it'd be 3, 0. So let's actually look at an example of analyzing these things. I'm going to get to this graph in a second, but I don't care about this level of detail. What I'm primarily concerned with is what is this thing's ultimate end behavior and where does it cross my x-axis. So ultimate end behavior is going to be based off of the degree. So I want to know what the degree of this thing is. As I look at it, this is really raised to the first. Although I don't see it there, it's a first degree. So here I've got a first degree x being multiplied by, now here this thing's being squared, so this would be a second degree x. If I've got this x that'll eventually hit this second degree x, that's the biggest x that this equation will create, and that's going to be x to the third. So here I have a third degree, and now I want to know the leading coefficient. The leading coefficient is important to me because I really just care, is this thing positive or is it negative? So I don't really care so much if it's big or small in terms of like a fraction or a very, very large positive number, or if it's small in terms of a really, really small negative or a very, very large negative. I just care one or the other, positive or negative. Here, my leading coefficient is positive. So now we should know what this thing is going to look like in terms of ultimate end behavior. So ultimate end behavior stuff is that this thing is going to be a positive odd degree. So I'll put this as odd. That's really what we're going for here in terms of figuring out what the degree is, whether it's even or odd. So here we see this is an odd positive, so it should be going down to -infinity on the left, and it should be going up to +infinity on the right. Now what happens in between is the stuff where these factors start coming into play. This is a factor, and this is a factor. So looking at the factor here in blue, it's x plus 2. So what is my 0 there? What's my k value going to be? I would solve and I would get k is going to equal -2. So again, just setting this thing equal to 0. So that means right here, we'll do a little 1, 2, throw a big circle. It crosses right there at -2, 0. And then I've also got this other one over here, which I'm going to get a k value of 1. Again, where's this thing set equals 0, solve for x? Boom. Here we go. So here's going to cross at 1. So this point is 1, 0. Now again, I just care about where it's crossing, and then ultimately what is it doing? Is it bouncing when it hits that point, or is it passing through? And here's how we do it. For each of the factors, okay, so for each one of these things, I just want to know, is it raised to an even or an odd? If it is even, whoops, there we go. That means it's going to bounce. If it is odd, whoops, not the best D, there we go. It is going to pass through. So here I'll show you what I mean by that. See this 1 here? That is odd. So this factor is raised to an odd degree. Because that factor is raised to an odd degree, when I get to this 0, I'm going to pass through. So instead of bouncing, I'm going to pass through that 0 there. Then when I get to this 0 here, it's an even degree. This is going to bounce. So I come back down around, hit this, and I bounce back up, and we see that we complete what we said what our ultimate end behavior would be. So again, the green arrows we started with is what we ended up with. Now, if you wanted to figure out what this y-intercept was, what color have I not used yet? Brown. So let's say we wanted to figure out our y-intercept. The y-intercept is pretty straightforward. We just plug in as x is 0. So that just allows us to solve for the y-intercept. We've done this a million times, so it's of a little less interest to me. So as I'm doing this, if I wanted to plug in 0 into this thing, what would it spit out? It would spit out 1/2. So if you were trying to find this y-intercept here, you just plug in 0 into your equation, see what you get for your y, and this one happens to be 0, 1/2. Now, I don't really personally care about this so much because we've done so much of it and it's pretty straightforward. I do care about ultimate end behavior, where it's going to bounce or cross through, and whether it bounces or crosses through. So again, in terms of what I would be looking for an answer, I would be thrilled to see a big circle there, a big circle here, arrow pointing down, comes through, hits this, bounces up, and sails off. That's all I'd be looking for. So again, if you want to find more points along there, you're able to. I mean, plug in as many numbers as you want. You can get it, pretty exact. But I really don't even have a y-axis labeled here because I don't care. The thing that's happening between these things and why it changes when it's odd is because as I progress through, so like no matter what x value I plug in for all this stuff over here, all of this junk is only ever going to spit out negative values for me. And then once I hit this point where it zeroes out, I start plugging in some slightly larger values, aka slightly less negative, and what happens? It crosses over from being a negative thing to a positive thing. Well, how is it that it crosses over? The reason that it's crossing over is it used to be that when I plugged in -2, it would spit out a 0. So when I pick a number slightly less than that, aka into this here, what's happening? Let's pick -1. As I evaluate -1 plus 2, it's a positive value. So again, our odd things are going to fluctuate whether it's positive or negative. So if it was positive and I raise it to an odd degree, it's going to remain positive. If it was negative and I raise it to an odd degree, it's going to remain negative. Said that right. If I look at my even degree things though, if before this was negative, like I have a negative sitting out in front of it, it's going to remain negative. And if I have positive sitting out in front of it, it's going to be positive as well. So again, this is with our even stuff. It's either going to open up in both directions or open down in both directions. So that's like where this whole change is coming from in regards to the even ones bouncing and the odd ones passing through. Here is a nice little summary I did at some point in class. I took a picture and uploaded here. So when we're looking at these crazy graphs, k is a 0. We have our factors. They look like x minus k. It doesn't mean that k is a negative value here. It just looks like this. So again, if it looks like x minus 2, k is really 2. If it looks like x plus 2, k is really negative 2. K is a solution in the polynomial equation when you plug in that x value and you get a 0. X-intercepts are just where it's going to cross that y equals 0 line. So here I'm going to introduce two new concepts, which is a local min and a local max. A local max is just where this thing kind of like pops up and then comes back down. And I'm going to show you how to find that in a sec. And then for local mins, it's the same idea, except for now we're going down and then pop back up. So when we're looking at this, we refer to these as turning points. So the turning points of polynomial functions, every graph that has a degree n has at most n minus 1 turning points. So say I was a 5th degree, then I'm only going to have at most 4 turning points. And it may not be that many. So really what it comes down to is you have n distinct real zeros, then you have exactly n minus 1 turning points. So if I had 3 different distinct zeros, I would have 2 different turning points. Here is what it would look like for my odd functions, okay? Here is an odd positive, and this is, I mean, besides just a linear thing like y equals x, this is our most plain vanilla. Here's the negative version of that below. So again, we see up to infinity, down to negative infinity. Here we see up as we go to negative infinity and down as we go to positive infinity. If I have crazy stuff happening, okay, whatever, it crosses at a bunch of points in between, but that's okay. And then again, crazy negative stuff is just a bunch of crossings in between. Ultimate end behavior is what I'm concerned with. Even functions, same sort of deals we've talked about before. Y equals x squared is our plain vanilla parent function. A negative sign out in front is going to have it open down in both directions. Now we're just saying, okay, make it crazy, but it's still positive even function. And let's make it crazy, but now it's still just a negative even function. Here we have the rules laid out for us in terms of ultimate end behavior. We want to know whether it's even or odd and whether the leading coefficient is positive or negative. We're going to have distinct zeros represented, and if it's even, it's going to bounce, and if it's odd, it's going to pass through. So here we have a couple more examples. If we want to find y-intercept, just plug in x is 0, but again, something we've done a lot already. So looking at this graph here, I see a list of factors here multiplied. It's nice that it's given to me already instead of me having to factor it. So here as I look at this thing, I get x plus 2, x minus 1, and x minus 3. Now this is really to the first, to the first, to the first. So since each of these is raised to the first, if I were to multiply all these things out, first I'd have to do binomial times binomial, and then I would do trinomial times binomial and do all that distribution. Now in doing so, I would eventually get x to the third somewhere, so that's my highest degree. So again, first is going to be a third degree. That's an odd function, so I care that it's odd. I don't see anything in front here, so when we don't see anything in front, it just means there's a positive 1. Cool, all right, that means it's a positive function. Now where are my real zeros? Where are my zeros? Well, here I got 1 at negative 2, 1 at positive 1, and 1 at positive 3. So here are the zeros, and we see them crossing at those points. Again, here's an odd positive function. It better go up to positive infinity as we go to the right, and down to negative infinity as we go to the left. Pass through, pass through, pass through, easy. On to the next one here. We have f of x equals, and now here I have a factor which is being squared. So again, when I have a factor raised to an even degree, we're going to see it bounce at that point. Here I have x minus 1 to the first and x minus 3 to the first. So the only thing we changed from this graph to this graph is I said, okay, now this one's going to be squared. So it changed it to a 4th degree, which is an even function. Still has a 1 as its leading coefficient here, so I'm going to be a positive even. I'm going to be going up to negative infinity and up to positive infinity as I go off. And here I'm going to cross at negative 2, 1, and 3. Now this crossing right here is going to be a bounce. So here I came down, I bounced right off, and then I'm going to come and pass through again, and I see I have my graph. Here we have a slightly cleaner version of where our turning points come in. Local maximums and local minimums here. I'm going to show you how to do it on the 84, but I'll also just highlight it in Desmos should you choose to do it there as well. We already summarized these turning points here. So here, when we're trying to find turning points, basically you want to graph your thing, and then from there you're going to go in and you're going to find these. Now, you don't know calculus yet, so we don't know how to find these in terms of taking a derivative, but what we do know is how to use a calculator. So what we're going to do is we're going to go first into y equals, and we're going to enter our equation. So we enter our equation in there, and then I'm going to go to my window, and I'm going to just make sure my window is set. Typically from -10 to 10 for x's and y's is the way to go, but for these graphs, a lot of them do get pretty crazy. So we just want to check our window. Again, I would just recommend expanding out, so like maybe from -50 to +50 might work for you, but it's going to vary problem to problem. So once I have my equation, I go to my window, just make sure that's good, and then I will go to graph. So now the calculator is going to graph it for me right before my eyes, and it's super cool. And then we are looking at what's going to be, oops, I already used green. So now I'm going to hit second, and then I'm also going to hit this button over here, whoops. Second trace, which is going to do calc for me. So I want to do second and then calc, and then I'm going to go down to the option which says either min or max, depending on what I'm looking for. So again, if I'm looking for like a local minimum, I'm going to do minimum. If I'm looking for a local maximum, I'm going to do maximum. Pretty straightforward there. Once I do that, I then am going to get flipped back to the screen that it has my graph on. So I'm going to pretend like there's a graph here, and it looks something like this. All right, so let's say I was trying to find a maximum. So in this example, I'm going to say for finding a maximum, what do I want to do? It's going to tell me to select a point to the left. Here's my maximum, it's right around here. I'm just going to scroll until I get about to here. I'm going to come hit enter, and then it's going to say, okay, right limit, and then I'm going to go over here clearly past where my top is, and I'm going to hit this as an enter. It says guess. I don't know why it says guess. Guess is just like this thing of, okay, you can approximate where it's going to be before it tells you. I think it's collectively wasted trillions of seconds of humanity's time. I think it's probably my biggest gripe against TI, but thank you for my mini rant. As we look at this thing, we just hit enter one more time, and it tells us our maximum. So it's going to spit out a point right here for us. It's going to tell us an x and a y, and that xy is our maximum. Likewise, we can do it for our minimum. We just want to make sure, again, we're to the left and then to the right. So if you did it for this one, it looks like it spits out local max of 0, 2, local min of 2, -2. So if you want to do it here, great. If not, we can always swap into Desmos, and Desmos has our local max here, 0, 2, local min here at 2, -2. So again, if you didn't have a TI-84 or didn't download the Calculate 84 app, you can do it in Desmos and some other programs as well. Here is a cool example of like an application of this. So in terms of application, again, we don't know calculus yet, but we can kind of tiptoe around that by using this min-max functionality on our calculators. So this is a box, and it's saying, okay, my box is going to be defined by taking just a rectangle and then cutting some corners out so I can fold the sides up. So I need my height on all these sides to be the same, and the width is going to be the same as well. So as I look at this, it's x by x, just defining that the wall is going to be whatever the height is, right? I don't want like some, wall over here that's going to be higher than the wall everywhere else. That doesn't really help me in terms of like putting things into that box. So when we look at this, we're going to cut x off of each here. So if this whole thing used to be 10, now it's going to be 10 minus 2x, and that's where we're getting our width here. And then we look at this, and our length used to be 15, and we're going to subtract off again 2x for the bits that we're cutting off of either side. So here I get my length. And then for height, it's going to be x itself, right? So as we cut this thing, it's going to be x inches high. Volume is just width times length times height, so I'm going to multiply these three things together, and I get some equation. So what is interesting about this equation is that this is modeling the volume of this thing. Now, obviously, I don't care about negative volumes because that's not going to exist. And so I'm going to stop here, and I would stop here. So again, only positive volumes allowed. And as I look at this thing, in terms of values for my x, the height here, the max height, is my maximum volume because I'm taking this and saying that is my volume. And my volume fluctuates depending on what the x is. So if you imagine cutting a super tiny x, you have super short walls, and you don't have very much volume in that box. But if you cut super tall x's, you would have essentially used up all of your space here, and you have a super tall narrow box. That doesn't help you either. So some sweet spot in between is going to maximize this thing, and what we would do is we'd use our calculator functionality of finding second calc and then max, and we'd again left bound, right bound to spit out this approximately 1.96, and then it ends up spitting out a volume of approximately 132. So in terms of how to maximize the volume of this box, we'd want to cut about 1.96 inches. So for most folks, that would be about a 2-inch cut. Just kind of one of the cool applications of this. You can maximize like size of a garden. You can do profit models as well. So there's a lot of cool stuff. And you can also talk about what the feasible range is. So again, like I can't cut more than 5 inches off of this thing because now my width has disappeared. So again, it's got to be less than 5 in terms of my x. So I can start by defining that sort of feasible region there. That is analyzing graphs of polynomial functions. Hope you enjoyed it as much as I did.